Hello, everybody. Welcome to our next round of IRIS-HEP Fellows Talks. First up, we have Aryan, who is mentored by Jim. Jim, can you say a few words about Aryan's work?
Well, Aryan's going to tell you about the details, but he spent the summer developing a new package. Rather than contributing to a larger piece of work, and it's quite impressive. Oh, he's an undergraduate at Manipal Institute of Technology, and it's been a pleasure working with him.
Hello, everyone. My name is Aryan, and I'm an IRIS-HEP fellow who's been working this past summer with Jim Pewarsky on this new library, as he mentioned. It's called fastjet, and it's a vectorized interface for jet finding in Python. Okay, so let's first talk about what fastjet is. So fastjet is a tool for jet finding in C++, and it's a really popular library. In fact, it's so popular that there are multiple interfaces for it already available, including the official bindings provided by the fastjet authors themselves. So let's look at the official bindings that the fastjet authors provide. Here you can see that these bindings, they require you to go over Python objects and loops. And as you can see here, if you want to construct a list of pseudojets, you have to go over the raw data in a Python loop. While this is acceptable in C++, it's a problem in Python because of the performance bottleneck that it presents. So we would, of course, be better off by eliminating it. So there are some wrappers that have tried to address this problem. One example is PyJet that partially solves this problem. What PyJet does is that it provides event-level vectorization, which means all the pseudojets are made into a NumPy array, which allows the user to use vectorized functions on it, which is good, but it only solves the problem partially. Because what happens often in jet finding is that analysis is done on a multi-event data. So what do you do with that? What do you need to handle this multi-event data? Well, you need something that can handle deeply nested and variable length lists. Something that can do that is awkward array. So also using awkward array saves us from frequent conversions between data types. So you don't have to convert it into a new Python object to use any other scikit-HEP tool. PyJet also has other problems. One of them is that it's based on a fastjet subset. So that means that it can give different answers than the real fastjet. Also, the PyJet interface diverges considerably from the C++ interface, which can be a problem because it sets a new standard. So given all this information, we decided to create, well, fastjet. It's a new package that aims to consolidate and address all the issues. And when I say a new package, what I really mean is that the official bindings have been packaged into a PyPy library, along with a new awkward array interface. Also, this marks the first time that the official bindings for fastjet will be available through PyPy. Okay, so this awkward array interface, how does it do things differently? Well, if you look at this graphic here, you can see that the classic interface has Python objects at the pseudojet level. So each of those small boxes that you see, those are pseudojets. But as you move along, you see that PyJet, this one big box, that's one whole event. That's how PyJet does things. It vectorizes on an event level. But we decided to take it one step further and vectorize the multiple events that we have. So you see that one big box, that's the one whole Python object that you can use. So it's a big improvement on the classic interface, while it's better than, of course, PyJet. So, okay, so what's the structure of this new interface? Well, this new interface really is two interfaces. One is the awkward array interface and the classic interface that have been packaged into one Python library. The classic interface is generated when the C++ library is compiled using Swig, and we take that interface and we pass it through as is. Also, the awkward array interface is a new interface that can handle the multi-event data. So if you look at this diagram that I have here, all these yellow boxes that you see, these are provided by the fastjet authors. The core C++ fastjet is there. That's the source of all the jet finding that we do. There's the Swig bindings, and then there's the Python interface, that's the single particle Python interface. On the other hand, you have the PyBind 11 bindings that have been written by me, and then they diverge into three different cases, where you have the single event, multi-event, and general structure case, which represents the three types of awkward arrays that this library can handle. So all of this goes up into the one single class that handles the awkward array interface, and then at the end you see everything goes into this one single user-side class that that the user can interact with. The user doesn't really interact with anything below in the private area, so the user doesn't have to worry about selecting the right kind of interface. That's done by the user-side class. Also, now you can get all of this through a single pip install. So that's a big departure from earlier when you had to get compile fastjet to get the full library and all its functionalities, which won't be the case anymore. Okay, so what's the classic interface? This interface that's provided by the fastjet authors, it works on by getting a list of pseudojets, as you can see here in this code snippet. This list of pseudojets is the Python equivalent of the vector of pseudojets that's used in the C++ interface. You make this list and then you pass it to the cluster sequence class along with the jet definition, and then you can extract data from this from that cluster sequence class instance. For example, like I've done here, I have tried printing the px values of all the inclusive jets in the event, and you can see that the information is being returned in the form of list of pseudojets. That's the case with the classic interface. Wherever there's the information to be returned is a list of particles, it will return a list of pseudojets. So moving on to the single event case in the awkward array interface, what you see here is again one event, but this time it's an awkward array. So this is a simple record array with possibly extra fields if the user wants it, and then everything else is the same. You make a jet definition and then you put it into the cluster sequence class instance. The only difference is how you define the data. So how do you extract data from the vectorized interface? Well, you do the same function call, inclusive jets, and then you extract the px values, and it returns an array of the px values of the inclusive jets. You can see that it returns an awkward array, not list of pseudo jets. So let's do a comparison with the classic interface. On a one-to-one comparison, you can see that, of course, there's no looping in the vectorized interface. And of course, the vectorized interface is much cleaner. Doing the same job is much easier in the vectorized interface. Okay, moving on to the multi-event case. Here you can define an awkward array with as many events as you like. In this particular example, the first event is same as the single event case. The second event here is empty. The third has 4 particles, and the last has only 1 particle. So this is how you define a multi-event case. And if you want to extract data from it, it's actually the same function calls as the single event case, but instead you get this deeper awkward array than the previous one because, well, it had multiple events. Another feature of this new library is that you might have seen that the multi-event input had the charge field, the extra charge field in it. Well, the thing is that the constituents of each inclusive jets, they're not really, that's not really a new any data. It's just a reordering of the original input. So since it's a reordering of the original input, you can preserve that extra field that you have, and you can, for example, what I've done here is sum over the charges in each individual jets, but you can really do anything you want with it because it preserves that extra field that you gave it. So another thing that you might have noticed is that we did away with the pseudojet class. It's not really there, and something has to take its place in the awkward interface. That job will be done by the vector library. And using the vector library is really easy. All you have to do is just import vector, and then you do a register awkward, which registers globally all your awkward arrays. And then you give your awkward arrays the name momentum 4D. What that does is that it specifies that this is a Lorentz vector, and now you can easily convert between one coordinate system and another. So all you really need to do is register your awkward arrays and you're done. So if you look at this particular instance, the coordinate system is PT eta 5 mass. So what we will do now is directly input this into the cluster sequence class. And as you can see, it takes it, no problem. It performs clustering, and then you get the constituents outputs. That's also in the PT eta 5 mass coordinate system. That's because, as I've said before, the constituents are just a reordering of the original input. So they'll be in the same coordinate system. Also, any particle data that is generated by the library will be in the Cartesian coordinate system. However, if you register your awkward arrays, you can freely convert between different coordinate systems. It's not really a big problem. Okay, so another upside of using the awkward interface is the scikit-HEP ecosystem. As I've mentioned before, it allows you to easily plug into this whole array of Python libraries that will make your life easier. So a testament to this fact is that there's already an analysis being developed using this new interface. This picture has been taken from the slides of Chad Freer. He made this presentation a while ago about this new analysis that he's developing. And as you can see in that red box there, the new awkward interface has been integrated into this awkward / uproot / coffee style analysis, and it works seamlessly. Another observation that Chad made was that if you look at the accuracy of this, it's really accurate. What they did was a one-to-one comparison with the old methods that they had. And as you can see, the red and the black lines, they trace each other so well that you can't even see the red line. If you'll have to look carefully, but that means that it's really accurate. The results are the same for both. So where does the difference lie? Well, the difference lies in the performance. What Chad observed and what he presented in the presentation was that there was a 20 times decrease in the wall time, and there was a 25 time increase in the throughput. So what happened was a 17-minute analysis went down to a 48-second job, which is really, really impressive. This analysis that I'm talking about is freely available on GitHub, and if you want to look it up, it's public and anyone can go and see it. Okay, so coming to the conclusion, there's only a couple of points I would like to make. First is that you can pip install fastjet now. Second is that it includes the classic interface, which is just the official Python bindings. And the vectorized interface overloads the classic interface with event at a time and multi-event at a time functions. It uses awkward array for arrays and vector for coordinate systems. It allows interoperability with the rest of the scikit-HEP ecosystem, and it's already being used in analysis. So thank you, and that was it from my side.
Thank you, Aryan. Are there any questions for Aryan?
Yeah, I actually had a couple. So this is extremely cool, Aryan. Yeah, I think this is going to be super useful. It's funny, I've been thinking about this exact problem in the last few days in the context of doing like machine learning tasks on jet problems. And I think it's going to be really important for machine learning because, of course, you want to batch over multiple events, right? Does it make sense to train these small jet events one at a time? So I was wondering if you'd thought about ways of plugging this into machine learning libraries that would really benefit from a kind of multi-event batch system? That's the first question. The second question is maybe more vague. I haven't quite thought it through, but we're using a kind of graph structure for a lot of these jets, and this is becoming quite a popular way of doing jet classification and so on. Is it clear to you if this could extend to treating events in a graph-like way, where you have a set of edges? Can awkward arrays handle that kind of structure?
Okay, so for your first question, well, the thing is that awkward arrays and really the whole structure of this library, what it does is it allows you to easily plug into not only the scikit-HEP ecosystem, but also the scikit-learn, or the bigger machine learning ecosystem. Awkward arrays have the functionality to turn to easily convert between one data type and another, so that you can really easily use the different machine learning libraries. Although I have to say I haven't explored the possibility of how, up to what extent you can integrate this into the machine learning workflow. But Jim Pewarski, my mentor, he's the developer of Awkward Array, and with some of the talks that I've had with him, it seems like this will be easy to plug into the machine learning ecosystem. And if you really want to explore more on this topic, I'm free to talk to you more about it. And could you repeat your second question? I forgot what it was.
So, does awkward arrays? Is there any way of capturing a kind of maybe it's a too difficult question, but because we treat a lot of these events as kind of like graphs, where each constituent jet is treated as some identity, and then the relationships between jets are treated as an edge, like a doublet, a node to node connection. Is there any native way that awkward arrays could handle this kind of structure?
That's really an awkward array question.
In fact,
I'm not sure how to answer it. It seems like Jim wants to say something.
Sure, I can take that. So actually, these are all great ideas, and this is exactly the kind of thing that we wanted this library to enable, but they're not the sorts of things that should be in this library itself.
Mm-hmm.
So yes, Aryan is not going to be building explicit connections to the machine learning libraries, but having the data in this form should make it easier to do that. Also, you'd want to bring into this your ideas of how you want to represent it in those libraries. So if you want to represent, say, a graph, you could do that in awkward array with an array of lists of index positions. And then those index positions, you can actually walk along the graph by applying those index positions as a slice onto the original array. But exactly how you want to represent that will depend on how you want to integrate it into the machine learning process. And so that's something we'd have to sit down and talk about, what representation. The awkward arrays themselves are trees, they're not graphs, but you can get the graph-like data by, enumerating indices.
Okay, that makes a lot of sense. Yeah, thanks.
Mm-hmm.
Okay, any other questions for Aryan? No? Okay. Thank you, Aryan. Thank you, Jim. Next up is Nupur, who is mentored by Carlo.
Nupur has graduated at University of Pennsylvania quite recently in 2021, and she has been working with LBL for the last 3 months. Her projects is within the so-called ACTS project, which is a common tracking software which is basically a generic framework and experiment independent open source software toolkit that takes care of track reconstruction, which potentially can be used in several experiments at LHC. And basically, a task has been to introduce machine learning algorithm approaches in specific points in track reconstruction in order to enhance performance, both from the CPU consumption point of view and physics efficiency. And specifically in the what we call ambiguity solver, which is the very last step of a track reconstruction in which you resolve candidates and hits wrongly attributed to the wrong tracks and so on. And yes, it has been a pleasure to work with her. She has been a great asset to the group.
Thank you, Carlo. I'm Nupur, and I spent this summer working on deep learning for ambiguity resolution with ACTS with Carlo and Professor Gray. So I'll go through the main challenges regarding ambiguity solving, a possibility for potential improvements, and importantly, how I approached making those improvements. So particle tracking in general, it helps us to understand the events that are occurring within a detector by providing that position and momentum information through a particle's interactions with layers of a detector. And this information is used widely. For example, to find muons, to identify the decays of heavy flavored jets, which are all components of analyses that help us search for new physical processes. So it's extremely important to have an efficient and a precise method for track reconstruction, and why it's such a strong focus for development in high energy physics. So as Carlo mentioned, ACTS was developed as an open source experiment independent tool for track reconstruction. So basically it attempts to resolve the impact of differences in detector geometries that really isolate the reconstruction algorithms in HEP experiments. By doing this, ACTS, it aims to become a useful tool for various HEP and nuclear physics experiments. So track reconstruction in ACTS, it's inspired by the algorithm used in ATLAS. So it begins with clusterization and space point formation, which creates 3D measurements or space points that represent where a particle interacted with the detector. Then seeding combines triplets of these space points, and that's used next in track finding, where these seeds are combined with other space points in many, many iterations, which gives us our track candidates. And then the final step is ambiguity resolution, which selects the final resolved tracks from our track candidates. So my focus was on the last step of this whole mechanism, and track finding, as mentioned, by iterating over those many combinations of seeds with other space points, it creates a very large number of track candidates, which results in fake tracks, which are just purely combinatorial collections of hits that don't correspond to a particle, and duplicate tracks, which are lower quality tracks that correspond to a particle. So we want to be able to distinguish these tracks from good tracks, which most accurately represent the trajectory of a particle. So in ATLAS specifically, this is done in an algorithm that assigns track candidates scores that are based on the reconstructed tracks, the track trajectories fit. And then it just returns the tracks with high scores. So the ambiguity resolution algorithm, it's a particularly large contributor to the overall track reconstruction time. With the upgrade of the high luminosity LHC, which will increase the number of collisions or pileup in the ATLAS detector, it's necessary for us to find a way to mitigate this complexity and optimize ambiguity resolution with this higher degree of pileup. And so then that brings us to deep learning. So neural networks that are implemented in this step of track reconstruction, they may have the potential to greatly reduce CPU consumption, but still continue providing us with high quality results. Currently, ACTS includes a simple neural network architecture that uses 3 track features to differentiate between good and duplicate tracks one at a time. And it has approximately 43% accuracy in recognizing duplicate tracks. So my objective was really to improve this accuracy by adding more track features and to extend this architecture to potentially include fake tracks and analyze multiple tracks at once. So using FATRIS, fast track simulation, particle trajectories for 1,000 TT bar events were simulated with a generic detector geometry, a pileup of 200, and a uniform 2 Tesla magnetic field. Track finding and fitting were then performed with a combinatorial Kalman filter that generated approximately 800,000 track candidates. 91.4% good tracks, 8.6% duplicate tracks, and 0.005% fake tracks. And let me explain how a track was labeled with this truth quality. So a track is a fake track if its truth match probability is less than 50%. And truth match probability, basically, it compares the number of measurements in a track candidate to the number of majority hits, which is the number of measurements that can be attributed to the truth particle that's associated with that track. So then for each truth particle, the track candidate with the maximum majority hits and the minimum outlier measurements is labeled as good. So the track features that I produced included the number of measurements, the number of outlier measurements, and reduced chi-squared fit of the track, which were used in the neural network already integrated into ACTS. And some new features that were introduced were the number of shared hits, which is the number of measurements also present in nearby candidates, the transverse momentum, the pseudo rapidity, and phi, which are both measurements of a track's location within a detector. So first, it's valuable to know, and I'll show how these features differ for the different track qualities. And since the number of fake tracks found in this data set was a very small number, its distributions were quite variable. So fakes are not examined in the upcoming few slides. So there is some small separation in the distributions of the number of measurements, the number of outliers, and the reduced chi-squared between good and duplicate tracks represented by the blue and orange bars, respectively. So as expected, the good tracks tend to have more measurements and fewer outliers, right here in the top right, and a reduced chi-squared closer to 1 here in the bottom right. However, there's much clearer separation in the number of shared hits distribution, which hints to us that this may be an important feature in helping us differentiate between good and duplicates. A quick side note about the shared hits distribution is that there was, it's important to point out that there was a smearing digitization issue when calculating the number of shared hits that has since been corrected since I finalized my results. But you'll see that my work is kind of independent of this, and the architecture of the algorithms I developed for ambiguity solving will still be effective despite this issue. So on this slide, we see in the top plot that duplicates dominate the distribution at high PT. And on the bottom left, they have symmetric peaks around -2 and 2 eta. However, the phi distribution here shows no discernible patterns between the good and duplicate tracks. So it wasn't used any further for ambiguity solving. So I mentioned that neural networks might be a useful tool for ambiguity resolution. And that's because they're often used in classification problems to recognize patterns in data to make predictions. So neural networks, they're made of one input layer that feeds in feature information to a hidden layer with a specified number of nodes that each apply transformations to this information using activation functions. And then this is then fed to the next hidden layer, which transforms the data again, or to an output layer, which returns our predictions. And neural networks learn to make the correct predictions by tuning parameters like the weights and biases that influence the transformations within a node. And tuning occurs as the losses, which are the measure of a prediction's deviation from a truth classification, are measured through backpropagation. So the ambiguity solving neural network architecture that I created analyzes one track at a time and consists of an input layer with 6 nodes for the 6 input features, 2 hidden layers, and an output layer with a sigmoid activation function, similar to a logistic function that returns the probability that a candidate is good. So this architecture was trained with 2/3 of the simulated events to reach an overall accuracy of approximately 96%. I specifically use a binary cross-entropy loss function to provide a measure of incorrectly classified tracks and an atom optimizer to serve as the backpropagation method. And 75% of the tracks were used to train the net and 25% were used to test its performance and tune hyperparameters such as the number of layers or nodes and activation functions. So 1/3 of the simulated events were used as the validation set to check the neural net's learning. So here, the receiver operating characteristic curve. It displays the signal efficiency, where a signal represents good tracks, versus background rejection, where background would represent duplicates. And here you can see that the ROC curve for the training and validation set are very similar, which means that the model is not overfit on the training data. Also, this steep shape of the curve means that the majority of output probabilities are either very close to 1 or close to 0. So in other words, for most tracks, the neural network is quite sure that a track is a duplicate or a fake. But to make our predictions, we take the output probability from the neural net and compare it to a threshold value. And if the output probability is above this threshold value, a track is classified as good. And using a metric called Udin's J statistic, which minimizes the difference between signal efficiency and background rejection, the optimal threshold for the validation set is found to be 0.67. So here I display the effect of using this particular metric in these confusion matrices, where the diagonal represents correctly assigned tracks. So by changing this decision threshold from 0.5 to 0.67, signal efficiency decreases by 1.7%, and background rejection increases by 12%. So as a simplification, I continue to use Udin's J statistic to evaluate my neural network performances in the upcoming slides. And at this particular optimal 0.67 threshold, good and duplicate track discrimination is 94.9%. It's important to note, though, that there's a clear trade-off between signal efficiency and background rejection when you're altering the decision threshold. So to extend the capacity of this neural network to include fake tracks, I altered the output layer to have 3 nodes and a softmax activation function, which is just a multi-dimensional logistic function, which outputs an array of probabilities that a track belongs to each class, good, duplicate, or fake. So the predictions are then made by classifying the track that has the highest probability. So just to test this architecture, I decreased the minimum number of measurements in CKF from 9 to 3 to generate more fakes, and this resulted in data set with approximately 4% fake tracks. And a separation in the feature distributions was most apparent in the number of measurements and the number of outliers distributions, where fake tracks in green here tended to have less measurements and more outliers. So after training this architecture, it was found to have the least discrimination for fake tracks, shown in the bottom row of this confusion matrix, where approximately 37% were labeled as duplicates. But although this architecture does not perform that well on this particular data set, a similar architecture can be put into place for a more realistic detector geometry that has a data set with more fakes. So I now want to introduce recurrent neural networks, which are a form of neural network that has memory. So basically the nodes within a recurrent layer use outputs from previous nodes to influence the next output in sequential data. And because of this function, RNNs are often used for inputs that are related to each other, like time series data, language translation, or recognition. And since RNNs are tailored to sequential data, they often support 2D input, or a sequence where each component has a set of features. So Long short-term memory networks are a type of RNN that are used for long sequence inputs, where traditional RNNs, they tend to suffer from short-term memory. And earlier inputs become less and less important as you proceed through analyzing a sequence. So one benefit to using an RNN for ambiguity solving is that it can handle data in series, so it can analyze multiple tracks at once. And to do this, the RNN input must consist of a sequence of tracks and their corresponding features, and the output would be the same series of tracks with quality classification. So since the number of tracks in an event could vary, input sequences would not be uniform. So I use sequence pre-padding, which pads sequences with an array of zeros as its feature values to make the number of tracks in an input uniform. But before creating and training this architecture, I considered different ways to organize track sequences. And I focused on ordering the input sequence by position within the detector using phi and eta so that the RNN could use nearby tracks to influence predictions. And I'll show 2 different methods I tried in a couple of slides. So the RNN architecture that I used consisted of an input that was sorted or grouped as decided, with a series of tracks represented by their feature information. Then I added a masking layer so that padded tracks are not considered in the training following in the following layers of the neural net. Then the recurrent portion of the net is a bidirectional LSTM layer with 100 units. The bidirectional wrapper on this layer basically it connects 2 hidden layers of opposite directions with the same output. So basically the RNN can learn from the sequence in both directions. The final layer was a time distributed wrapped dense layer with a sigmoid activation, which returns an array of good track probabilities. And the time distributed wrapper simply allows the RNN to return an output probability for every input. So RNN performance here is shown for an input where tracks in an event are grouped by phi and eta into 9 equal width bins. And then each bin sequence of tracks was used as a separate input for the RNN. So after training, the RNN was run on the validation set to find an optimal decision threshold of 0.72. And if the RNN output probability for a track was greater than this threshold, the track was labeled as a good track. So for this model, good and duplicate track discrimination shown by the confusion matrix was 95.9%. And then I would just like to note that variable width equal size bins for each event or lesser number of bins yield the same results. But if more bins are used, the input sequences become too small and the performance actually worsens. A simpler organization for the input was also tested, where the tracks in an event were simply sorted by phi and eta. So the RNN was analyzing all of the tracks in an event at once. And this resulted in an optimal decision threshold of 0.74 and a good duplicate track discrimination of 96.1% at this threshold. And this was the best performance seen across the neural nets tested, a consistent 1.2% increase over the RNN with bin input. And then although I had chosen to try binning this data to reduce sequence length that the RNN needed to handle, it appeared that the RNN was suited fairly well to larger length sequences. And in terms of the simple neural net, we see a 1.2% increase in track discrimination from 94.9%. So similar to the neural net, I also aim to extend this architecture to handle fake tracks by altering the time distributed wrap dense layer to have 3 nodes to return a matrix of values, the probability that a track belongs to each of the 3 classes for each of the input tracks. And looking at the confusion matrix, you can see again in the bottom row that this architecture has the least ability to recognize fake tracks, labeling approximately 30% as duplicates. So again, although this architecture doesn't perform that well on this modified data set, with a data set generated for other detector geometries that has more fakes, a similar architecture can be put to use effectively. So within ACTS, I mentioned that a neural network with 3 input features is already in place to label duplicate tracks using an Onyx runtime plugin. So ONNX is an open source format that stores models for different ML frameworks, including TensorFlow and Keras, which is what I used. And once a model is stored in ONNX format, ONNX runtime allows inferencing using that model across different platforms. So the ONNX runtime plugin in ACTS, it's currently configured for a neural network with one input and output node. In other words, it can only support a net that analyzes one track at a time right now. So just to update the current configuration within ACTS, I uploaded my simple neural network in ONNX format, and I added 3 input features: the number of shared hits, transverse momentum, and eta to the function in CKF that ran inferencing on my model to label duplicate tracks. So just to preliminarily validate my model and my changes to ACTS, I ran CKF twice on the same set of simulated particle trajectories. Once where truth information was used to identify duplicates, and one where my neural net was used. And in this plot of duplication rate versus eta, which is generally consistent with, you can see here an approximately 15% lower duplication rate. And that's generally consistent with the duplicate track recognition of 85% found for a 50% decision threshold. So for the future, I think this implementation can be further verified by comparing the predictions made in CKF using the neural network to that made by TensorFlow and Keras directly. And another potential project could include integrating the RNN framework into ACTS by expanding the current configuration for a network with more than one input and output node. And to increase access to more fakes, the architectures that have been presented can also be trained and altered and adapted to data sets generated for other detector geometries, including ITK and Open Detector. So thank you everyone for listening. I can take any questions.
Thank you, Nupur. Any questions for her? No? Okay. Next up, we have Varun, who was mentored by Daniel. Daniel, have a few words you want to say about Varun's work?
Sure. Yeah, Varun has been with us for a few months at the as part of the Exatrix project, which uses graph neural networks and graph techniques for doing track reconstruction. And with Varun, we've been focusing on TrackML style data sets and tackling one of the big parts of our pipeline that has really been bottlenecking, which is constructing the graph and how to handle these huge event graphs effectively. And so he's been looking at a few kind of novel techniques on how to do that. And I'll let him take it over.
Sure. Thanks, Daniel. I'm Varun. I'm from UW-Madison, and I've been working as an IRIS-HEP fellow for the last 3 months with Daniel on this project of graph methods for particle tracking. So I'll just give a brief introduction into the problem that we were solving. So as we all know, the Atlas and CMS experiments generate large volumes of data, and reconstruction of the particle trajectories is a critical component of the data analysis pipeline in high energy physics. And the Exatrix group has been investigating the use of graph neural networks as a solution to the problem. So what we were doing is we have a heuristic that is used to generate edges between hits that are thought to come from the same particle, and then have a GNN classify the edges as real or fake. And this allows us to construct, the results from that allow us to construct a full track candidate. So the dataset that we used was a TrackML CodaLab dataset comprising of 9,000 events. and 100,000 hits from around 10,000 particles. So I specifically looked at two stages of the pipeline. The first one being the processing. The processing involves calculating cell information features and constructing truth graphs. The cell information features are features that provide information about the direction of a charged particle. And as for truth graphs, as the name goes, it basically contains the true edges that connect hits from the same particle. The next stage that I looked at was the embedding, which involves learning a distance metric for the hit measurements that are embedded into a new Euclidean space. These ensure to be low enough such that the embedded space is not sparse, not too sparse. And the other thing in the embedding that was crucial was the application of the nearest neighbors algorithm to create the predicted graph. I'll be going into more detail with that. So here's a diagram that just shows what the embedding looks like. So here on the left, we have the original space and a set of hits. And we then go to the embedded space. We then use the nearest neighbors algorithm to generate edges between the hits to reconstruct the track. So here's a list of the cell information features from the processing stage that I ended up using at the end. I'll explain why I chose these features. So I looked at this image, and this section involves investigating the use of cell information features. I looked at 3 set of models, one that was generated without any cell information, one that was generated using raw cell information features, which are used to compute the final cell information features that are listed above. So I looked at how important the inclusion of cell information features is. This is a efficiency purity graph, and one variable that you can't see here is the radius. The efficiency and purity both change as the radius changes, and the trend is that as the radius increases, the efficiency increases and the purity decreases. So I like to, as a CS major, the way I looked at it was I looked at efficiency and purity as basically precision and recall, purity being precision and efficiency being recall, if that makes it easier to understand. The critical thing to know here is that there is significant improvement going from no cell information to using the raw cell information features, which included features like the thickness, the pitch, which were part of the Coda Lab dataset. And then going from the raw cell information to the calculated cell information features, there's substantial improvement as well. So that justified the inclusion of using the cell information features. So I'll move on to the embedding stage. This is a set of tasks that I performed in the embedding stage. One was to update the build edges function in the embedding pipeline. I will be explaining the build edges function soon. By integrating the fixed radius nearest neighbors and replacing Facebook's face library, face algorithm, and then choosing the right loss function, studying the impact of weighting edges, performing hyperparameter scanning to obtain the optimal hyperparameters, and then using these hyperparameters to train the final MLP. So the build edges is part of the embedding pipeline, and the role that it does, it calls the appropriate nearest neighbors algorithm, generate edges and build a graph. The input for the build edges function is the set of query points, that is the set of hits for which we want to query the database of points for and then generate edges for. And then the database of points, which is the set of all hits in the event, the Rmax, which is the search radius within which we want to generate the edges, and the Kmax, that is the number of neighbors we want to explore within the search radius, and the output is the graph. So the fixed radius nearest neighbors algorithm is this is a library that's written by Li Xin, who's a researcher over at Zurich. And this is a search that's implemented on CUDA, and the reason we use this is because it provided us a significant speed up over Facebook's phase and PyTorch 3D KNN. So this was integrated in the build edges function that I mentioned before. And this is a critical part because we need this to do hard negative mining. Hard negative mining basically involves appending false positives to the training set while training to help the model learn better. And the other things that I did in the with the fixed radius nearest neighbors was perform a couple of tweaks, such as not performing the KNN to speed it up even further. And then finally, the benchmarking results showed that the FRNN, with the tweaks that we made, performed at a speed that was 10 times faster than Facebook's phase. I'll be displaying the graph soon. So this is just a visualization of what the FRNN looks like. It basically uses grids to speed up the search. So here's a graph that details the benchmarking. This is just a one graph from a set of graphs. So here I looked at the time taken against the dimensionality of the points. So I used 100,000 points, a K of max of 1,500, and an R of 1. Note the R is only required for the fixed radius nearest neighbors and not the face or PyTorch 3D. As you can see here, the FRNN provides a significant speed up relative to both phase and PyTorch 3D. Then the next thing I looked at was choosing the max K for the FRNN. As we saw about, max K is the input for build edges, and this is also subsequently an input to the FRNN algorithm. And we want this, and we need this because in order to achieve high efficiency, it's important that we have a max K value that is greater than or equal to the number of neighbors for a point that belongs to the densest region in the embedded space. So you can't arbitrarily set this to a high value because of memory constraints. So I looked at specifically 3 algorithms to understand, to obtain a value for max K, one of them being KD3, one being dbScan, and then the other one was simply using the FRNN grid, the inherent features present in the FRNN grid to determine the max K value. The KD3, what I did with the KD3 was to randomly sample a set of points from each of the leaf nodes and then perform a radius search using the scikit-learn library to obtain the number of neighbors for the specific point from the leaf. And then I I've then found the maximum number of neighbors that you could generate for a specific point from a leaf node. And then the maximum number was basically what I set my max K to. As for the dbScan algorithm, this is a density-based clustering algorithm. I quite simply, I use QML for dbScan, and I quite simply found the densest cluster and chose, and set my max K value to be the number of labels associated with this cluster, basically the number of points in the densest cluster. The FRNN grid solution, I used the inherent features that were present in the FRNN grid. One of them being grid count. I used the grid count to determine the densest cell, and then I identified all the points that belong to the cell and ran the fixed radius nearest neighbors on this on each of these points using an approximation for a K value that was just set. I just specifically set it to around 10,000, and I ran that. And then I chose the max K value to be the number of the maximum number of edges that were generated for a point that belongs to the densest cell. Then the next part was to choose the right loss function. since we are using this distance metric, we want the distance metric, we want the positive examples, which are the true edges, we want to minimize the distance between the embedded hits. So penalization is supposed to increase as the distance between these the hits from true edges increases. For negative examples, which are the false edges, we want to maximize the distance between the embedded hits. So you want to apply more penalization as the distance between these hits decreases. So I looked at two loss functions to do this. One was the binary cross entropy loss and the hinge embedding loss. I've just attached the description for the hinge embedding loss and the binary cross entropy loss. In the interest of time, I won't go into looking at them in detail. So this is a graph demonstrating the result that I got. So clearly the hinge embedding performs better than the binary cross entropy loss. So that's the loss function I chose to stick with. The next part that I looked at was the inclusion of weighting while training. So the weighting functionality that's present in the embedding pipeline is to prioritize more important tracks. So you have weights associated with the with tracks. The high weight tracks tend to be longer and comprise of more hits relative to the low weight tracks. As you can see, I've just included a few hits, few tracks in this image. The red tracks are the high weight tracks, and the blue tracks the low weight tracks. And to assess the results from weighting, I replaced the vanilla efficiency and the vanilla purity metrics with the weighted efficiency and weighted purity metrics to get a better understanding of if the model actually is able to recover the high weighted tracks recover the high weighted tracks better than the unweighted model. So this is the formula that details the the weighted efficiency and weighted purity metrics. True weights are, I'll just describe what the true weights and the pred weights are, since the weighted efficiency and weighted purity are quite straightforward to follow. So the true weights is the average of the space points, of two space points that are represent the edge. So, and the pred weights is the average of the two space points when the edge is a true edge, and it's just one if it's a false positive. So we have a weight assigned to each of the space points based on how, based on what weight, based on the hits that we want to recover. So that was assigned. I did not have a role in assigning that. I just used all pre-assigned weights. So this is a comparison of how the weighted model performed compared to the unweighted model, that is the model trained with weighting and without weighting. So as you can see, the weighted model performs significantly better relative to the unweighted model. Although at higher efficiency, the improvement achieved, the weighted model relative to the unweighted model is not that much, but it's still better. So this is over weighted efficiency and weighted purity, by the way. The other thing that I looked at was the hyperparameter scanning. That is to understand how the impact of varying hyperparameters such as number of hidden layers, number of hidden nodes, the K for hard negative mining, etc. And I used Daniel's strain track library that allowed me to iterate over multiple hyperparameters and generate models in a serial and trackable fashion. And then this helped me get the optimal hyperparameters for the configuration of the embedding pipeline. That is whether we are training with noise, and the set of rules for selecting the hits. And as you can see, this is just a scan plot that just shows how the models compare. So this is the final architecture that we used for the final configuration. That is, we were training with noise at the end. So this is the final MLP architecture that we had. And that is it. Thank you very much.
Thank you, Varun. Any questions? Jim, you have your hand raised?
Yep, just a quick one about the activation function. I remember does it matter which S-shaped function it is? Because I remember Tanch is one of the most expensive to compute. So
yeah, that's true. I did not specifically look at the activation functions to use for the embedding pipeline, but I'm sure that you could maybe use some other activation functions, but yeah, I did not quite explore whether to change the activation function for the MLP. So I can't really comment on that.
Okay, that's all. Thanks.
Any other questions? All right. Well, thank you everybody for coming. Thank you to all the fellows for your talks. They were great today, and thank you to all the mentors as well. We have some talks upcoming. I believe the next one is a sort of a one-off next Tuesday, which I'll send out an announcement about. So thank you all. Bye.
Thanks. Bye-bye.